Welcome to this video lecture. In this video lecture, we are going to talk about the Vernier Calipers. This is a complete tutorial of the Vernier Calipers. I will take you through the major parts of the Vernier Calipers. Then we'll talk about the three main functions of the Vernier Calipers. And then we're going to talk about the theory behind the Vernier Scale. And then I'll take you through the process of reading the scale. So let's go straight to the parts of the Vernier Calipers. So when it comes to the parts, I'd like you to observe that there is a part of this Vernier Calipers which is moving and the other one is fixed. So this one is referred to as the sliding jaw. Let's name all the parts as in this figure here. So like we have said, this sliding part, the whole of it, including this other part which comes over the end here, is referred to as the sliding jaw. And then there is a fixed jaw, that jaw which does not move. Now, then we've got outside jaws. One of them is on the fixed jaw, the other one is on the sliding jaw. And then of course we've got inside jaws. Again, one is found on the fixed jaw, the other one on the sliding jaw. Then when it comes to scales, there are two scales. There is one scale which is found on the fixed jaw. It is referred to as the main scale. And there is a scale which is found on the sliding jaw. It is referred to as the Vernier Scale. And then of course, there is a lock nut here. When we want to take measurements, we usually lock the sliding jaw onto the fixed jaw, and that allows us to take the reading. Now let's go to the three main functions of the Vernier Calipers. But before we do that, you might want to pause the video and name the parts of the Vernier Calipers from A all the way to G. Okay, let's go ahead and look at the three functions of the Vernier Calipers. And we start with a situation whereby we want to take external dimensions, e.g. the external diameter of a cylindrical rod. Here we've got a cylindrical rod. All that we'll do is to open the jaws and then close them like that. Then lock the nut, read the scale, and it will be equal to the diameter of this rod here. So it can be used to take external dimensions, and this is just an example. Let's see how it can be used to take internal dimensions. For example, there is this hole here, or it may be a gap, or it may have any shape, but it cannot be measured using the external jaws. That means we'll have to use the internal jaws, and we just need to move our Vernier calipers inside like that, and then open the jaw so that the inside jaws are able to press onto the sides of this object. And by reading the scale, again, we'll be able to tell the length of this dimension here. So it can be used to take internal dimensions, e.g. the internal diameter of a hole or a depression. Let's look at the third use. The third use makes use of this part here, because you realize that when the jaw is moving, there is a part which is coming out at the end of the Vernier calipers. Let's say maybe we've got this object here. There is a narrow hole somewhere here. So what we'll do, we will align it like that and then move the sliding jaw until it touches the bottom. So that allows us to measure the depth of that hole. For example, it may be a hole, it may be a step, or any other shape which cannot be conveniently measured using the inside jaws or the outside jaws. So those are the three functions of the Vernier calipers. Now let's go ahead and look at the theory behind the Vernier scale. This is the Vernier scale. We want to compare it with the main scale. So at this point, let's zoom in so that we can study this part of the scale, this region here. So I think this is good zooming in. So we've got the two scales. This scale here, which is on the fixed jaw, is referred to as the main scale, while the scale on the sliding jaw is referred to as the Vernier scale. Each one of these scales has 10 spaces or 10 divisions. In fact, this is 0, and then this is 1 centimeter. So from here to here definitely is 0.1 centimeter. How do I get that? I get 1, I divide by 10 spaces. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 spaces, each one of them is 0.1 centimeters. So this length here is 0.1 centimeter. Next, I want to determine the length of this division here, because you can see, other than the first mark, the 0 mark on the main scale and the 0 mark on the vernier scale, they coincide. But when it comes to the second mark on the main scale and the second mark on the vernier, you can see that they do not coincide. So definitely this length here is not equal to that. As a matter of fact, it's a bit shorter. This one here is a bit shorter. How do I determine that length? It's very easy. I look at the whole of this from here all the way to this point. What is the length of this distance here? I just need to compare this length with the main scale here. We know that if this is 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. I stop at this point because I can see that this mark coincides with this mark, as well as the 0 mark here coincides with the 0 mark here. So I can comfortably say that the 10 divisions on the vernier scale occupy a distance equal to 0.9 centimeters on the main scale. So that is how I get this length here. I just need to compare those divisions. So this length is 0.9 centimeters. So in order to get the length of one division on that scale, I just need to divide this by 10. So what I'll do, I'll get 0.9, divide by 10, and I get 0.09 centimeters. So the length of one division here is 0.09 centimeters. You can see obviously it is shorter than the length of one division on the main scale. And indeed, for me to get 0.1 centimeters, remember I did exactly this. I got 1 centimeter and then I divided that by 10 divisions and I got 0.10 centimeters. Let me add that other 0 there so that I can make this one to be 2 significant figures. Now, what is the difference between the length of one division on the vernier scale and the length of one division on the main scale? In other words, this difference here. So I'm going to zoom in further so that you can be able to see what I'm referring to. This difference here is what I want. And in order to get that length, I just need to get the difference between 0.1 and 0.09 centimeters, and I get 0.01 centimeters. This value here, this one, is very important to us. It is referred to as the least count. Let me explain what we mean by count. When we count numbers, we usually count like this. You can count 1, 2, 3, 4, and so forth. We are moving in terms of 1. We are adding 1. So our count here is 1 because we are adding 1 onto the previous number in order to get the new number. Let's look at how we count these divisions here until we get here. We start with a 0, then the next division is 0.1, 0.2, 0.3, 0.4. Now what is our count here? If you start with a 0, of course even here we started 0 and then we went to 1. Here we start with a 0, we go to 0.1, 0.2, 0.3, and so forth. You can see that we are counting in terms of or our count here is 0.1 centimeters. Here we were counting in terms of 1 centimeter. So that is how we count this. Now, how do we count these ones here? How do we count them? We count 0.09, 0.18, 0.27, and so forth until eventually we get to 0.9 centimeters. That is how we count that. But that is not what I'm talking about. What I'm talking about is this least count. Now imagine moving this sliding jaw through a distance. Okay, before we do that, I'd like you to observe that in this particular position, this division or this mark on the vernier scale coincides with the 0 mark on the main scale, while the 10th division on the vernier scale coincides with the 0.9 centimeter mark. The other divisions in between, they do not coincide. Look at them carefully and you will see that they do not coincide. Now, which is the next ones to coincide? Which are the divisions which appear as if I were just to move the sliding jaw through one step to the right, they are going to coincide. Through one step to the right. Of course, you can see that it is these two that will coincide. So, if I move this sliding jaw through a distance just equal to 0.01 centimeters, because that is the difference between the two lengths, if I move it through a distance equal to 0.01 centimeter, then this division will coincide with that. And because the sliding jaw has moved to the right, the gap created here will be equal to 0.01 centimeter. Now, in that particular position, once these two have coincided, the next two divisions which are likely to coincide if I move the sliding jaw to the right through, again, another distance of 0.01 centimeters will be this division here. These are the ones which are going to coincide next. So it's very important to observe that. So you can see that I'll be moving the sliding jaw in steps of 0.01. The next one will be 0.02. The next one will be 0.03 centimeters and so forth. That is what we mean by a count. I've shown you a count when we use whole numbers, shown you a count when we use one decimal place, and I've shown you the count when we use two decimal places. So because this one is the smallest, has got the smallest value, we are counting in terms of the smallest value. That is where the word least comes in. Our count has got the smallest value, so it is referred to as the least count. So having understood the idea behind the least count, remember the least count is the difference in the length of one division on the main scale and the length of one division on the vernier scale. Now, why are those important? Let's look at the following slides. Now, when you look at this slide closely, you will see that the coinciding division, the 0 mark on the vernier is coinciding with the division here, and the 10th mark on the vernier is coinciding with the mark 1 on the main scale. Those two coincide. That means that this mark here has moved to the right through a distance equal to the length of this. So this gap here is 0.1 centimeter. So this one has also moved through 0.1. The difference between this edge and this edge is also 0.1. Remember, If we had an object here, maybe we had a small cylindrical rod somewhere around here, the diameter of that rod would be 0.1 centimeter. And if we had a gap here, small gap, and that is what we are trying to measure, the depth that we are trying to measure, the depth would be again 0.1 centimeter. Again over here, the same thing. So by reading this scale, we are determining the distance between these two edges, either between the two inside jaws, the two external jaws, or the length of this bar when it is being used to measure the depth of a hole. So that is 0.1 centimeter. So the reading here is 0.10 centimeters. How will 0.20 centimeters look like? This is how 0.02 centimeters looks like. And you can see this one has moved through 0.1, 0.2. It is exactly 0.2 because this mark and this mark, they are coinciding. And the other marks in the middle do not coincide at all. So that means the gap between these two jaws is exactly 0.2 centimeters. Now let's see whether you can be able to determine this other reading here. How about that reading? State the reading and then I'll show you how it is determined. Okay, let me show you how we do that. First of all, I check the position of this mark here. Remember, it was here when the two jaws are closed. This mark was exactly here. So it went through 0.1, 0.2, 0.3, 0.4, all the way up to 1, and then it went beyond. So that means I get 1, I add 0.1, so I have 1.1, and then I have 1.2. Before I can say whether it is 1.20, 1.2 something, I need to check whether these two divisions are coinciding. And the moment I see that this mark is coinciding with the mark there, and this one is coinciding with the second mark here, and the middle divisions are not coinciding, then I'm very comfortable in saying that that is 1.20 centimeters. So far we are looking at readings where the two marks on the vernier at the edges are coinciding with marks on the main scale. That allows us to read up to the first decimal. So the second decimal is obviously going to be 0. Now how about if the ones at the edges do not coincide? Let's look at an example of that. And here we have such an example. If we zoom in, you will be able to see that the marks at the edges do not coincide. This one does not coincide with this. This one does not coincide with that, because if they were to coincide, then this thin division will be at the center of the thickness of this one. And because it is at the edge, it means they don't coincide. That means there is supposed to be a mark here which is coinciding with another mark here. Can you be able to identify that mark? Let's check. These two do not coincide. These ones don't. They don't. They don't. They don't. But you can see the distance is becoming smaller and smaller. They don't. They don't. And they do coincide here. This is number 1. This is 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is number 1 mark on the vernier which coincides with the mark on the main scale. I get that 1. I multiply it by the value of the least count. I get 0.01 centimeters. And then I go back to the scale. I ask myself, where is the position of the 0 mark on the main scale? The position of the 0 mark of the vernier on the main scale is between two numbers. Obviously, it is greater than 0.1 because this one is 0.1. So it is between 0.1 and the next number is 0.2. So it is greater than, that value is obviously greater than 0.1. I think this is how we write it. Our reading x is greater than 0.1, but it is less than 0.2. I think we can write it like this. X is greater than 0.1, but less than 0.2. That is how we can write it. So we are not so sure whether it is 0.11, 0.12, 0.13, because all these are the possible values all the way to 0.19. So one of them must be the answer. So it is 0.11, 0.12, 0.13, all the way up to 0.19, which is the answer. It's very easy to get that. You come to this inequality here and choose the lower value, or the smaller value, 0.10. The moment you decide, let me repeat that because it's very important. The moment you decide the position of the 0 mark on the main scale, and how do you do that? You look at where it is. You ask yourself, this mark is between two numbers on the main scale. What are these two numbers? You write down the smaller number and the higher number, and then you choose the smaller number. That is all you need to do at that step. And then at that point, you will go to this value here. You add it onto this one. You add. And definitely when you do 0.10, which is this one, plus 0.01, you get 0.11 centimeters. And that is how we would get the actual measurement of this scale. So I'd like you to take your time and state the readings of the scales which I have given in the exercise which follows this video lecture.